This is a homework question from the Unit 3 Lesson 2 homework assignment. It's number 13 on one of your classmates' homework. The question ID is 13.6.016 from the Larson and Edwards Calculus Early Transcendental Functions textbook. We're asked to find the gradient of the function at the given point, and we're given this function and we're given this point. And so it really comes down to knowing what the gradient is, finding all the parts of that gradient, and then just evaluating it at a point. So let's start by stating what the gradient is. So we're just going to state the formula for the gradient. And remember that that's represented by del G. And since G is a function of two variables, the gradient will be a function of two variables. So we're going to state that formula. And remember that the gradient is a vector with as many components as you have variables. So this is a function of two variables. So this is a vector with two components. Oops, I used F instead of G. So I have the partial of G with respect to X there, and the partial of G with respect to Y there. So we just need to compute this partial derivative and this partial derivative. We'll substitute those in, and then we will evaluate those at the point 19, 0. Okay, the next thing we do is compute the partials. You could represent the partial of G with respect to X that way, or you can represent the partial of G with respect to X that way. Or you can use this operator notation, that's the partial with respect to X of our function. So I look at this and I say to myself, what rules from Calculus 1 apply to this when taking the partial with respect to X? Now I notice right away that I've got a function of X over here times a different function of X. So this is our first function and this is our second function. So I'm gonna have to use a product rule. So we'll have the derivative of the first function with respect to X times the second function plus the derivative of the second function with respect to X times the first function. Now this is a pretty easy derivative, and that's a pretty easy derivative. You just have to remember that y is being treated as a constant and we're differentiating with respect to x anytime you take a partial with respect to x. The derivative of a constant times x with respect to x is just the constant, so this is 14. And this is an exponential, and it's not just e to the x, it's e to the y over x. So I've got an exponential with a function of x inside. That means I have to use the chain rule, the Calculus 1 chain rule, in order to evaluate this partial derivative. So remember from Calculus 1, if you're taking the derivative of a composite function, so that's a function nested inside another function, you use the chain rule. And the chain rule says you take the derivative of the outside function first, and I'm going to think of that as the inside function. The derivative of e to some power is e to that power times the derivative of the inside with respect to x, treating y as a constant by the chain rule. So this is e to the y over x times the partial with respect to x of that inside function with respect to x. Now you can leave it like this and do the algebra later, but I think it would be easier if I did the algebra right now. So instead of writing y over x here, I'm going to bring that x up to the numerator. When I bring it up to the numerator, that changes that positive 1 power to a negative 1 power. And what we get is x to the negative 1 times y, or y to the negative, or y times x to the negative 1. Either one is fine. So I have e to this power times the derivative of the inside, and I'm taking the derivative of this function now with respect to x. y is being treated as a constant, and I'm taking the derivative of x to the negative 1. The derivative of x to the negative 1 times a constant is that constant, so y, times the derivative of x to the negative 1. The derivative of x to the negative 1 is negative 1 times x to the negative 2 power. Okay, so we've got all the pieces there. Now, initially it might look like you've got a lot going on here, and you kind of do, but remember, each of these is multiplying each other. So basically what we have is 14 times e to the y over x, and then I have a positive, and I'm multiplying it by this negative. So I have positive times a negative is a negative y, and then I've got an over x squared, that's one factor, times 14x, that's another factor, times e to the y over x. And one of these x's will reduce. And so what we get is 14 e to the y over x minus 14y over x times e to the y over x. Or if you prefer, you can factor out the e to the y over x. And you get 14 minus 14y over x times e to the y over x. And if you're not sure, you can always distribute that back through. This times this gives us this, and then this times that gives us that. So that is the partial with respect to x of our function g. I had to use a product rule, and then we had to use the chain rule within the product rule. Now you want to be very careful here. Whenever you're taking a partial with respect to x, you treat y as a constant and differentiate with respect to x. When we take the partial with respect to y, which is what's necessary for us to do next, we have to treat x as a constant and differentiate with respect to y. So let's do that. So you could write that as the partial of g with respect to y, or the partial with respect to y of 14x times e to the y over x. Now, remember, we're treating x as a constant. So as far as we're concerned, this is really just a constant times an exponential involving y. So remember, if you're taking the derivative of a constant times a function, the first thing you do is you just bring the constant down, and then you differentiate that function with respect to y, treating x as a constant again. And again, I don't just have e to the y, I have e to this power involving y, so I have to use the chain rule. The derivative of e to some power is e to that power times the derivative of the inside with respect to y, treating x as a constant. And I will rewrite that again, bring that x up to the numerator. That's going to give us x to the negative 1 times y. But don't be distracted by the x to the negative 1. As far as you're concerned, x is a constant. Like that could be a 3. This could be y divided by 3. Or this could be 3 to the negative 1 power, or 1/3 times y, same thing. So I'm taking the derivative with respect to y of a constant times y. The derivative of a constant times y is just the constant. And so we've got that. So 14x times e to the y over x times x to the negative 1. You can write that as 1 over x if you prefer. I'll write that as one fraction as well. That way we can see there's an x in the numerator and the denominator, and those reduce. And so we just get 14 times e to the y over x. So our gradient function, the gradient of g, is a vector with these two components. The first component is 14 minus 14, actually I don't remember, 14y over x times the exponential. And the second component is the partial of g with respect to y, which is right here. So we substitute the partials into the gradient function. And the last thing we were asked to do is evaluate this at a particular point. I believe it said evaluate this at x equals 19, y equals 0. And we're in Calc 3. I think we all know how to evaluate something at a point. Just in case, we are literally replacing y with 0 and x with 19. And this is e to the y over x, so that's 0 divided by 19. This is 14 times e to the 0 divided by 19. And of course, e to the 0 is 1. So we have 14 minus 14 over 19. Oh, actually, that's going to be 0, sorry. We have 14 times 0, which is 0 over 19. And then 14. So our vector ends up being the vector with components 14, 14, or if you prefer, 14 times I hat plus 14 times j hat. Either one of these should be fine in WebAssign.